that we are getting here is an indication of that to say the final solution is basic or alkaline. Okay, so here they say to identify the metal M in an unknown metal carbonate, MCO3, the following procedure is carried out. So here we can see that we have the carbonate, and carbonate is CO3 2 minus. So already we are expecting this metal to be in group 2 on your periodic table. Yes, of course, just by looking at that formula. So here they say the following procedure is carried out, and it happens in 2 steps. In the first step, 0.198 grams of impure metal carbonate is reacted with 25 cubic centimeters of 0.4 mole per cubic decimeters of nitric acid. In the second step, the excess nitric acid is then neutralized with 20 cubic centimeters of 0.15 mole per cubic decimeter barium hydroxide solution. Then they say, assume that the volumes are additive. Well, I'm not really sure what they mean in the context of science. I'm not sure what that statement means. But these are the 2 reactions for each step, of course. The most important thing we can realize in step 1 is the fact that the 0.198, we can't really say is the mass of this metal carbonate because they tell us that it is an impure metal carbonate. So it's the mass of the total sample. It means the mass of this metal carbonate is less than the 0.198 grams. And we also know that the acid is going to be an excess reagent, and the other one is going to be neutralized. The one in excess is neutralized by the barium hydroxide. It's what we call a back titration in grade 11. Yes, there was a 10-mark question that we did with the grade 11s for back titration. So it's the same thing. Now, what do I mean by back titration? I mean that you are reacting 2 reactants, and one of those reactants is in excess. It remains after the reaction is finished. Then you don't want it to remain. You just take it and you react it with something else. So yes, it's back titration. The reason why we say it's back titration is because you now have to go to the second reaction and then move backwards in order to find information about the one in the first reaction. So we are moving backwards, actually. Right. Well, the 2 reactions are already balanced for us, so it's all good. Then the first one says we need to define a strong base. Well, you can do that. And they're asking us to calculate the number of moles of barium hydroxide that reacted with the excess nitric acid. Okay, well, let's quickly do that. So in other words, we are now in the second step. That's the most important thing. Right. So, well, with regards to this barium hydroxide, we are actually given the concentration as well as the volume, so we can easily find the moles by defining the concentration, of course. So we say, well, the concentration of this solution is defined as the number of moles divided by the volume. Then this concentration is 0.15. We are looking for the moles, and the volume is given in cubic centimeters. So we need to convert it to cubic decimeters. So we divide 20 by 1,000, and we simply get 0.02. Yes, of course we do. Then in order for us to find these moles of barium hydroxide, we just cross multiply, in which case we simply get 0.003 moles. So these are the moles of barium hydroxide that reacted with the nitric acid. But it's not the moles of nitric acid that reacted with barium hydroxide. Okay. Then the next question says we need to calculate the pH of the solution after step 1. And it's very important to understand this. After step 1, which means before we do step 2, right? Yes, after step 1, before we do step 2. Well, even if you don't say before we do step 2, but it's after step 1. So after step 1, we know that nitric acid was in excess. That's the most important thing. Before we reacted this with barium hydroxide. I hope you get what I'm saying to you. Okay? So then, now that we know this acid is in excess, then we need to find the number of moles of the acid that are in excess. So how can we get the moles of the acid that are in excess? Well, it's very easy. We just need to relate these number of moles of barium hydroxide to those of the nitric acid. But we are doing this in step 2 because step 2 is the one that tells us the moles that are in excess. But Rona, we know deep down in our hearts that we are finding the pH after step 1 before it reacts with the barium hydroxide, because the barium hydroxide is going to neutralize it. So which means after it reacts with barium hydroxide, we won't be having anything that is in excess. Right. You can still state the relationship as we did with this question by saying something like this, something like what? I'm not sure what I want to say. Yes, something like this. You can relate them like this, or there's another way to relate them, right? What is that other way? Well, if we look at the mole ratio in step 2 between nitric acid and barium hydroxide, well, the relationship is 2:1, which means the number of moles of the acid are twice as much those of barium hydroxide. So that's what you can say. And say the number of moles of nitric acid are twice as much the number of moles of barium hydroxide. This is the second way of stating the relationship. And just say it's twice 0.03 if you don't want to write it like this. It's a shortcut, really. And then you'll now say, well, the number of moles will be 0.06 moles. Well, I haven't got the space, but you need to write the unit as well. So, yes. So now we know the number of moles of the acid that are in excess. Then we can easily find the concentration of this acid that is in excess. And here I need you to be very, very careful. So how do you become careful? Well, remember, we are saying after step 1, before step 2. So you need to go to step 1 and say what is going to be the volume of the solution. So if you look at it in your step 1, you're only given the volume of one reactant, which is the acid itself, the 25 cubic centimeters. That's what you are given. You don't know what is the volume of this metal carbonate. So it means in solution, the total volume will be 25 cubic centimeters in step 1. So that's what you'll be using. So when you'll simply come and say, okay, fine. The concentration of the nitric acid, the one that is in excess, right, is equal to the number of moles divided by the volume. Well, maybe can specify that it's in excess. So the number of moles is 0.006. The volume is 25 cubic centimeters. And when you find this ratio, well, you find that the concentration is 0.24 mole per cubic decimeters. Okay, fine. So nitric acid is a monoprotic acid, which means it will only produce or rather donate one proton when it ionizes in water. So this means the concentration of the acid will be exactly equal to that of the hydronium ions. So then you can just tell them that the concentration of the hydronium ions will be equal to that of the acid. And this is equal to 0.24 mole per cubic decimeter. Then knowing what you know, you can now come and say, well, the pH is the negative logarithm of the concentration of the hydronium ions. Then you can say, well, this is what you are having. And when you find the negative logarithm of this, you simply get 0.62. Yes. This should be the pH of your solution after step 1 and before step 2. Now, next they say to us, the percentage purity of the metal carbonate, which is a solid, in the sample is 85%. Okay. Identify the metal M. Well, that's fine. So how can we identify the metal M? What is this most important thing that we need to find in order to identify the metal? Can anyone tell me? You can just turn on your microphone and tell us. What is it that you need to calculate in order for us to be convinced that metal M is this? Well, no one volunteers, so I'll have to ask a person. What do you think, Nosipo?
So I didn't quite hear you when you asked the question.
Okay, my question was, here they're asking us to identify the metal M. So what I'm asking is, what is it that we need to calculate in order for us to convince them beyond reasonable doubt that metal M is magnesium, for instance? Yeah, I didn't hear what you said.
So don't you need to find the molar mass?
The molar mass. Thank you so much, Hansi. The molar mass, yes. So, under normal circumstances in grade 10 as well as 11, they used to ask you to calculate the percentage purity. That's what they used to ask you. But now they give you the percentage purity and they ask you to move backwards. Right. Okay. So then how can we find this molar mass? Well, it's very easy. In order for us to find the molar mass, we need to know what is the mass of this metal carbonate in this entire sample first. And how can we find that mass? Well, we are going to find that mass by using this 85% percentage purity. Well, I think that's where we can begin firstly. So let's go ahead and do that. One thing we learned in grade 10 is that if we want to calculate the percentage purity, we are just going to take the mass of the compound. So I'll just say the mass of this metal carbonate, and we divide it by the mass of the entire sample. Well, in this case, we can just say the mass of the sample. That's perfectly fine. And then we times this by 100. So here we are given that the percentage purity is 85. We need to find the mass of this metal carbonate, but they told us the mass of the entire sample. They said it's going to be 0.198. And of course, we times this by 100. So what's the easiest way to do the math? Well, the easiest way is to multiply both sides by the reciprocal of 100, or divide both sides by 100 if you like. So that we get 0.85 here. And here we still have the mass of this metal carbonate divided by 0.198. Then now we need to cross multiply. So when we say 0.85 times 0.198, well, we find that the mass of this metal carbonate will be 0.1683 grams. Okay, fine. So now that we know the mass of the metal carbonate, we just need to know the number of moles of this metal carbonate. Then we can easily find the molar mass of the entire compound. Then from the molar mass of the entire compound, we can now subtract the molar mass of this CO3. But the question is, how do we find the number of moles of this metal carbonate? Well, it's very easy. We just need to know how many moles of the metal carbonate were needed in order to react with the nitric acid. That's all. And if you remember well, we already know the number of moles in excess for this nitric acid. So we just need to find the number of moles that were available at the start of the reaction. So that knowing those two, we can now easily find the number of moles that reacted or those that were needed to react with the metal carbonate. Yes. So let's go ahead and find the number of moles of the acid which were available at the start of the reaction. Because we already know those that are needed, or rather, those that are in excess. Sorry about that. So, well, we were given the concentration as well as the volume of the acid in step 1. Yes. So we need to define concentration of a solution. And they said to us in step 1, we have 0.4 mole per cubic decimeters of nitric acid. And the volume was given to us as 25 cubic centimeters, which when we properly convert to cubic decimeters, gives us this much. And when we cross multiply, we find that the number of moles of hydrogen nitrate, which were available at the start of the reaction, will simply be 0.4 times 0.025, and we simply get 0.01 moles. Okay, fine. So we know the moles that were available at the start. We also know the moles that were in excess. Yes, we found that 0.06 moles were actually in excess. So now we just need to find those that were used to react with the metal carbonate. So here we can say, well, the number of moles that were needed to react with the metal carbonate will simply be those that were available at the start minus those that were in excess. And of course, if you say 0.01 minus 0.006, you find that 0.004 moles were used to react with the metal carbonate. But this doesn't mean that this number of moles of the metal carbonate reacted with the acid. No. These are the moles of the acid that are needed to react with the metal carbonate. But how many moles of the metal carbonate are needed to react with the acid? Well, you can now state the relationship between the acid as well as your metal carbonate. But remember, it's not compulsory for you to say this. You can also use the way that I showed you before. So, well, here we can see that we have 0.04 moles of the acid. So then how many moles of this metal carbonate? Well, half the number. So you simply take this one, you divide it by 2, and you times it by this one. Then we can see that the number of moles of our metal carbonate will simply be 0.002 moles. Okay, fine. So now we know the number of moles of the metal carbonate. We also know the mass of the metal carbonate. Then we can just state our formula and say the number of moles, they are equal to the mass divided by the molar mass of the entire compound. Or if you like, you can say this entire compound is made up of the molar mass of this metal plus carbon plus 3 times oxygen. But it's much better if you do that towards the end. So generally speaking, let's say it's the molar mass of the entire compound. So now we have 0.002, and here we have 1683, and this is divided by M. And if you make the molar mass the subject, you just divide by 0.02. So 0.1683 divided by 0.002, well, we simply get 84.15 grams per mole. 1683. Yes. All right. Then where to from this point? Well, we know the molar mass of the entire compound, but we know that this compound is actually made up of a certain molar mass, which we don't know, plus the molar mass of carbon, and 3 times the molar mass of oxygen. And this will be equal to 84.15. Then when you say 84.15 minus 12 minus 3 times 16, well, we simply get 24.15 grams per mole. Yes, and it's to 2 decimal places, yes, but on the periodic table, we know that The element that has a molar mass of 24, that is going to be magnesium. So this means our M, it's just going to be Mg, which is our magnesium.